Chapter 2: Humanity Awakening to Space. When a man is called, he is often called young. I was 9 years old when my future whispered in my ear and changed my life. Looking back from the vantage point of 94 years of active life, I have no doubts about when and where it happened. On January 3rd, 1950, my parents took me to New York to visit the Hayden Planetarium for a birthday surprise. I was interested in astronomy, and a dozen other things. I had read several short guides to the sky and enjoyed them, marking the tables of information on the planets with exclamation points and question marks. But I paid special attention to the gaps in the tables, where the word unknown appeared, where the authors had inserted question marks after certain entries. When we arrived at the planetarium that evening, I was prepared to listen and learn. We watched the planetarium shown on the January sky with avid interest, and I stayed after the crowd had left to pepper the speaker with questions about the moon and Mars. On the way out, we passed by a meteorite display featuring a large pitted piece of metallic iron. I explored it animatedly, trying to imagine where and how it had formed. Suddenly, a jolt like an electric shock ran up my spine. I stiffened and became utterly still. My mother looked at me strangely. "What's the matter, Tommy? Don't you feel well?" I caught my parents by their arms, and I stared at the meteorite, gathering my thoughts. I slowly turned to look at them with great intensity. "Someday, I'm going to be very, very rich." My parents glanced at each other in puzzlement. Later, in the car on the way home to New Jersey, I drowsily reviewed the highlights of that evening. I remember I was humming a little tune to myself as I lay outstretched on the back seat. "Dad." "Yes, Tommy." "There's something else I learned tonight." "You mean besides you getting rich?" "Yes, someday I'm going to go where that meteorite came from." But the strangest tale is yet to tell. I was right. From How the Future Was Won, the autobiography of Thomas L. Duncan, Cosmos Press, St. Petersburg, Specialist Cinquecential Edition, 2091. Western culture was born into a tiny universe in which the Earth was the center of creation. The Sun, the Moon, Mercury, Venus, Mars, Jupiter, and Saturn orbited about the Earth. According to Ptolemy, writing in the 2nd century AD, in strange patterns of nested circles and epicicles, their motions, no matter how complex they appeared, had to be analyzed in terms of superposed circles, because circles are the purest and most perfect geometric form. These 7 celestial wonders, planets from the Greek word for wanderers, were regarded as perfect, immaterial spheres, and complete and immutable set. No one knew bodies could be added to this list because 7 is a mystical number, the first unobvious prime, a sign of completeness and perfection. When Galileo, observing the heavens in 1610 with a newly invented telescope, claimed the discovery of 4 large moons in orbit around Jupiter, his conclusion was unacceptable. Prominent churchmen concluded that the telescope, therefore, had to be an unreliable instrument. In fact, it had to be a tool of deception sent by the adversary to lead humans to question the church's authority. Evidence from telescopic observations, therefore, had to be deemed inadmissible. Indeed, since the church held that the heavens were perfect and divine in origin, any observation at odds with that theory, such as mountains on the moon or spots on the sun, had to be rejected. Just beyond the realm of the moon, sun, and planets, the story went, there are a great black vault pierced by a myriad of tiny holes. Beyond that vault was the celestial kingdom, a world of pure light, whose presence was revealed to us only by those tiny holes in the vault of heaven. The entire physical universe, in this conception, was only a few times larger than the distance from the Earth to the Moon. Light could cross this universe in a few seconds in modern language. We would say that the universe was a few light seconds in diameter. The planets, being immaterial, perfect spheres, had to be featureless. Questions such as what made the craters on the surface of the Moon, how old are the volcanoes on Mars, and what is the atmosphere of Venus made of, could not be answered because they could not even be asked. The modern reader must wonder how such transparent nonsense could survive in a single glimpse of the complex, tortured surface of the Moon. But so entrenched was the equation of the physical heavens with the spiritual, perfect heavenly realm, it was necessary to dismiss the features seen on the Moon as a simple reflection of the Earth on the Moon's surface, like a mirror-like surface. Medieval texts even attempted to correlate the face of the Moon with the map of the Earth. The dark areas of the Moon were taken to correspond with Earth's seas, a notion perpetuated to this day by the Latin name Maria, meaning seas, given to them. The stars, being imagined as tiny holes in the dome of the firmament, had all had to be the same distance from Earth. Although no secure means to measure the distances of the planets and stars yet existed, it was widely accepted that the universe was 100,000 to a few million kilometers in diameter. By the time the 17th century, Dutch physicist and astronomer Christian Huygens discovered a method for measuring the speed of light by careful timing of the ellipses of the satellites of Jupiter. He found that the known solar system spanned at least 2 billion kilometers, a distance that would take light about an hour to cross, not just a few seconds. What then were people to make of fireballs, meteorites, comets, meteor showers, and other heavenly spectacles not accommodated by the theory? It was necessary to deny that they were planets, since the number of planets had to be 7. Meteorites could not have been of celestial origin because the heavens were perfect and immaterial. Certainly not the kind of place where ugly rocks might have been found. Meteorites, therefore, had to be an atmospheric manifestation, native to the Earth. A popular theory of the 18th and 19th centuries held that they were made in the upper atmosphere by condensations of gaseous exudates from Earth. Because of the association of that most meteorites fell with brilliant celestial firework displays and loud thunder-like rumblings, it seemed likely that these gas exudates somehow ignited and burned high in the atmosphere, giving rise to meteorites as the ash of violent combustion processes. Others held that meteorites were more immediately terrestrial in origin, being akin to volcanic bombs ejected by violent eruption events. But in the late 18th century, the infant science of chemistry concluded to cast doubt on these ideas, repeatedly finding that meteorites with compositions that differed strikingly from all known types of terrestrial volcanic rock. Comets presented a more serious problem. They could not be a mere local atmospheric phenomenon because they could be viewed from half the Earth at the same time. They, in some sense, had to be celestial. They were also esoteric, erratic, and unpredictable. They appeared unforeseen, changed dramatically in position and appearance in a short time, and then vanished. The general opinion was that comets were immaterial, spiritual portents sent by the Creator as a warning about impending momentous events. A voluminous, highly spirited, and utterly contradictory imperative literature grew up around comet apparitions. A common interpretation of the appearance of a new comet was that it was a sign of the impending birth or death of some great person, or of an impending victory or defeat in battle. A comet appeared at the time of the death of Julius Caesar. The appearance of a bright comet in 1066 is immortalized in Bayeux's tapestry and connected by tradition firmly to the Norman conquest. In his famous Asteroids of Magi, 1303, Goethe reflected the medieval obsession by inserting a comet in the scene of the birth of Christ, drawing on the 1301 apparition of Halley's Comet for his first artistic inspiration. Deaths occurring months or even years after the appearance of a new comet were assigned to these portents. Indeed, some great comet sightings were even linked to events that had occurred months or years before the comet appeared, making them very poor portents indeed. In no correlation with great events was obvious, then there was simply shortcoming of part of the human observers as ignorant interpreters of the divine mind. The tendency of meteor showers to occur in the same parts of the sky on the same day of different years suggested to some scientists that they were in fact following orbits around the sun and were subject to prediction. Nonetheless, great feats of mental gymnastics were performed to make them into atmospheric phenomena. Their tendency to reappear at fixed times of the year was attributed to seasonal variations in the release of punitive exudations by the surface of the Earth. The prominent series of meteor showers seen each August when people were most likely to be outside at night was cited to argue that extras were baked out of the ground by the heat of the summer. The annual cycle of faint meteor showers in November and the occasional apparitions of spectacular showers in that month in the intervals roughly 33 years were sometimes admitted as embarrassments to the summer exudation theory. As astronomers came to appreciate the differences between stars, planets, comets, and meteors, the true architecture of the heavens began to emerge. The stars were clearly more distant than other bodies, but more precise understandings had to await the invention of techniques for measuring their distances. A more modern awareness of the real relationship of Earth and the solar system, stars, and the universe first dawned in the public imagination in the early 19th century, on the heels of the American and French revolutions. In 1838, the great German mathematician Friedrich Bessel reported the first crude measurements of the distance of one of the nearest stars, 16 Cygni. That distance was roughly 600,000 times the distance from the Earth to the Sun. Many other distance measurements where relatively nearby stars soon followed. Viewed at such immense distances, even the Sun itself would have been only about as bright as the faint-looking stars in the night sky. Those stars must then, in fact, have been as bright as the Sun, to be visible over such distances. The conclusion was astonishing. The universe must be so large that it would take light many years to cross all of known space. Each star in the sky was in fact the Sun in its own right, possibly attended by its own family of planets. The laws of Newtonian physics and mathematics might then apply to and help us understand a vast larger universe we hitherto thought possible. The Church, both Catholic and Protestant, endorsed the authoritative opinion of Aristotle that the heavens and earth were of different nature and obeyed entirely different laws. Isaac Newton himself thought this theory of universal gravitation showed that, contrary to Aristotle's view, one law of gravitation applied to apples and the moon alike. Some were exhilarated at the prospect of an immense universe whose properties, scope, and laws could be uncovered by the tools of science. Alexandra Pope wrote, "Nature and nature's laws lay hid in night. God said, 'Let Newton be,' and all was light." Others found the idea threatening. The 17th century French savant Blaise Pascal recoiled from the prospect of a vastly larger universe centered neither on the earth nor its sun. "The eternal silence of those infinite spaces terrifies me." How Pascal could have recoiled from the modern measurement of the universe. What would he have said if he had known the vast starry realm known to him but a tiny corner of an immense island universe of stars? The Milky Way spiral galaxy, tens of thousands of light years across, containing several 100 billion star systems. And how would he have reacted to the knowledge that there are billions of other galaxies compared to our own, spanning distances out about 16 billion light years from Earth? The volume of the universe known today is roughly 10 to the 27 times as large as that which terrified Pascal. What was the role of humankind in this new vast universe? The cozy dome of sky and crystal spheres of the Plutonic universe, all firmly centered on the Earth, affirmed humanity as the central fact and the focus of creation. But Copernicus shattered the crystal spheres and put the planets in orbit around the sun. Then Bessel banished the stars to immense and terrifying distances. Discoveries of the 20th century then exiled the sun to the sparse outer fringes of the Milky Way, a rather typical spiral galaxy, just among billions. As it became accepted that the bodies of the heavens were material objects, not spiritual beings, extension of Newton's laws of motion, first to the moon and the planets, and then to the stars, became possible. Physics gave us the Bill Bradley's phrase, a sense of where we are, but also a sense that the laws governing our motions in space were the same ones governing the planets. Modern astronomy, while operating an immense gulf of space and time between us and the stars, at the same time established a world in which we were all the stars, all played by the same rules. The gap between a spiritual heaven and the materials on Earth, formerly unbridgeable, had now shrunk to a manageable proportions. It was now only a physical gulf that separated us from the moon and the planets, and even the stars. True, that gulf was still very large, but the physical gulf between the continents had loomed equally large in the minds of 15th century geographers and explorers. From Earth to the moon was indeed further, but to certain visionaries of 19th century technology, the gap was of the same kind as which separated the continents. It was not until the general acceptance of the material nature of the heavens that it became possible to even conceive of the space travel. Early literary portrayals of space, such as Daniel Deoff's The Consolidator, 1705, had insufficient contact with reality to give them any credence as predictions, being little more than fantastic settings for political and social satire. The very idea of space as hard, deep vacuum was unfamiliar to some early writers. As recently as the early 1900s, it was common for the means of propulsion used to reach other worlds to be physically fanciful, lifted by the sun's attractive force upon vitals of the dew, or utterly non-physical, transported to Mars as in a dream. It was with the birth of modern science, engineering, and science fiction that the actual means of travel and survival in space became accessible to rational discussion. Jules Verne envisioned From the Earth to the Moon in 1865, a giant cannon built in Florida and based on Civil War military technology to propel a sealed spacecraft to the moon. We know today that firing this gigantic gun would have utterly crushed its delicate human occupants, but at least Verne attempted to propose a specific physical method to fire vehicles into space. He imaginatively conceived of a moment of weightlessness experienced by the astronauts as they passed through equal gravity points between Earth and the Moon. As a matter of fact, actually once free of the retarding frictional effect of the atmosphere, occupants of the projectile would remain weightless right up to the moment of impact with the lunar surface. Not long after, H.G. Wells postulated physical means of travel between the planets in his War of the Worlds. The idea that technology could actually make the heavens accessible to humans dates only from the beginning of last century, and the pioneering and independent work on rocket propulsion by the Koningstad Trivolsky in Tsarist Russia, Robert Goddard in the United States, and Hermann Oberth in Germany. Tsiolkovsky was born in 1857 in the village of Iazkosko in Russian Ryazan province. A severe bout of scarlet fever as a boy left him deaf that he was unable to attend school. Homeschooled by his parents until the age of 16, Tsiolkovsky read voraciously and developed a lifelong fascination with mathematics and physics. Having exhausted the educational opportunities of his village, he was sent by his parents to Moscow to study chemistry, astronomy, mathematics, and physics. There his studies led him to the reading room of the Tverskov library, where he fell profoundly under the influence of the philosopher Nikolai Fyodorov, a cataloger at the Goddard. Fyodorov was the most prominent of the astonishing philosophy. Fyodorov was a proponent of an astonishing philosophy that envisioned the perfectionism of mankind, the raising of the dead, and the settlement of the cosmos. When young, Tsiolkovsky's health deteriorated after 3 years in the harsh Moscow climate. He returned home to become a teacher of mathematics and physics in the village of Borovsk at age 24. He wrote several original papers on gas kinetic theory, which he sent off to the St. Petersburg Society of Physics and Chemistry. The eminent chemist, Dmitry Mendeleev, responded personally, informing Tsiolkovsky that the ideas he sent forward were valid, but that they had been published in England some 20 years early. Sensing Tsiolkovsky's intellectual powers, he nonetheless strongly encouraged her to continue his research interests. Working alone in the early 1880s, while employed as a schoolteacher in Kalag, he pioneered the theory and experimental testing of lighter-than-air craft. His interest then turned towards engineering and psychological problems of spaceflight. He explored the mathematics and physics of rocket propulsion at a time when no one had the means to carry out the experiments to test his ideas. His greatest work, published first in 1903, was the exploration of cosmic space by means of reaction motors, the world's first monograph on rocket propulsion. In it, he develops the mathematics of rocketry and introduced the idea of the step rocket, in which several stages are fired sequentially to achieve orbital velocity and eventually escape velocity from the Earth. Until 1920, his work remained utterly unknown outside of Russia. Experimental work on rocket propulsion did not begin in Russia until long after the 1917 revolution, when Tsiolkovsky was already an old man. The Goddard Hydrodynamic Research Organization, a private group dedicated to testing and developing flight rocket hardware, began operations in the early 1930s under the leadership of M.K. Tikhonov and Sergei Kirov. The latter was to achieve lasting fame as the chief designer of the Soviet space program in the 1950s and 1960s. Tsiolkovsky himself never received a kopeck of government funding until he received a pension. Tsiolkovsky envisioned the conquest of space in 14 points. The first few concerned elements of basic rocket technology of little interest to us here. Point 5, unmanned orbital flight, was to be followed by Point 6, manned orbital flight, and then by the development of a spacesuit and its use for spacewalks. Next was to come the development of space agriculture for use in orbiting space colonies, and the use of solar power for transportation and power in space. Once the technology to operate in space was in hand, humankind would turn to the exploration of asteroids and use them as the basis for an industrialization of space. Tsiolkovsky's 14th and final goal, echoing Fyodor's visionary philosophy, was the perfection of humanity and society. Robert Goddard, born 1882 in Worcester, Massachusetts, first developed interest in rocketry and space travel as an undergraduate at Worcester Polytechnic Institute. After receiving a PhD from Clark University in 1911, he stayed on as an assistant professor to teach and to pursue largely theoretical research on rocketry. By 1909, he was already aware of the superior potential of liquid hydrogen, liquid oxygen rocket engines. In a manuscript, Robert Hutching Goddard, born 1882 in Worcester, how do you pronounce that? Massachusetts, first developed an interest in rocketry and space travel as an undergraduate at Worcester Polytechnic Institute. After receiving a PhD from Clark University in 1911, he stayed on as an assistant professor to teach and to pursue largely theoretical research on rocketry. By 1909, he was already aware of the superior potential of liquid hydrogen, liquid oxygen rocket engines. In a manuscript written by Goddard in 1918 and kept sealed at his insistence for 54 years, he envisioned the expansions of humans into space through the use of space materials, culminating in the construction of a vast fleet of nuclear-powered asteroids that would carry mankind to safely from the death throes of the sun's countless years in the future. In 1919, his vastly more conservative monograph, A Method of Reaching Extreme Altitudes, was published by the Simonthith Institute. It was variously regarded by its readers as either brilliant or deluded. By 1920, Goddard, like Zhabotsky before him, had turned to the theory of liquid-fueled rockets as the most promising means for launching Earth satellites. In the 1920s, he struggled to raise funds for actual construction and testing of small liquid-fueled rockets. Amidst an atmosphere of mixed hostility and skepticism. Nevertheless, the Godheim Foundation came forward with the funds necessary for Goddard to begin flight testing in New Mexico. Even as his work bore fruits with successful test flights, his first small rockets in 1926, Goddard was pillared as moon mad, a crackpot in an infamous editorial in the New York Times. Goddard's research on the mathematical and physical basis of rocket propulsion clearly demonstrated that performance of rocket engines improves significantly when they are fired in the vacuum of space. He also developed quite independently of the earlier but inaccessible work of Zhabotsky the theory of multi-stage rockets. It is interesting that Goddard's achievements were not in any way dependent on the government foresight and vision. It was Goddard Foundation, not government bureaucracy, that saw the promise of Goddard's work and invested in it. The first government support for the work that Goddard was awarded in 1960, 50 years after his death, when the US government was found guilty of infringing his basic patents and was fined $1 million. Hermann Oberth, born in 1894 in Höchstadt, Transylvania, then part of the Austrian-Hungarian Empire, studied medicine, mathematics, and physics in Munich until being called into military service during World War I. In 1915, he presented the design of a long-range liquid-fueled rocket to the Austro-Hungarian War Ministry, which rejected his idea as fantasy. After the war, Oberth moved to Heidelberg to study with the outstanding chemists and physicists there. In his doctoral dissertation, completed in 1922, he developed the mathematics of spaceflight and demonstrated how a rocket could be fired to reach escape velocity of the Earth. In that same year, he heard, for the first time of 1919, monograph by Goddard, with whom he became correspondents on matters of mutual interest. His brilliant doctoral dissertation was rejected by the University of Heidelberg, but Oberth was so convinced of its worth that it had to be published in 1923 at his own expense. In 1925, its publication brought to him correspondence that informed him of the existence and work of Zhabotsky, and they began to correspond. Oberth's book, Wert zur Gemeinschaft, Routes to Space Travel, published in 1927, won the International Hirsch Prize for tens of thousand francs, which Oberst immediately applied to experimental research on rocket propulsion. That book contained a proposal for electronic propulsion of spacecraft, a technique we now know as ion propulsion. The publicity surrounding this book also stimulated the newly formed 1927 Vera von Raumschat, literally the League for Spaceship Travel. The succession of this organization in firing small liquid rockets in turn attracted the attention of the government army well before the outbreak of World War II. The Bundeswehr was recaptured not so much because of the obvious merits of rocketry, but because of the Treaty of Versailles, which placed very severe restrictions on the development of German artillery, but failed to mention rocketry. Following Goddard's first flight test of a liquid-propelled rocket in 1926, events accelerated markedly. Stimulated by Goddard's success, the American Interplanetary Society was founded in 1930. The AIS was later to become the American Rocketry Society and functioned more as a trade organization than a research and education foundation. The Vigorous British Planetary Society was founded in 1933. Thus, by 1933, 4 leading technological powers of the world had all established non-governmental organizations for enthusiasts dedicated to building and testing rocket hardware and exchanging ideas about humankind's future in space. Progress in rocket performance closely followed establishment of these organizations. In 1931, Goddard held the world altitude record for a rocket, with a flight to 1,700 feet. By 1933, the Soviet Grid group had flown a rocket 1,300 feet. And in 1934, the ARS fired a rocket over a horizontal distance of 1,338 feet. With Wehrmann funding the 8,000 marks, and German team fired a small rocket, the A2, to a height of 1.5 miles in 1934. In 1935, Goddard fired 2 rocket engines to 1.8 and 2.8 miles. The German success stimulated the infusion of 11 million marks from the Luftwaffe in Wehrmacht in 1935. In 1937, a large new test range was opened on the island of Planetary in the Baltic coast. By 1941, Adolf was at Pinonin. The rocket engineer was at the rocket testing place. Development of military rockets was proposed to Hitler in 1939 and rejected by him on the basis of a bad dream in which a rocket had failed to work. Working on a shoestring budget, the Budweiser rocket team carried out a successful test flight of the A-14 rocket in October 1942. A movie of the test flight was immediately sent to the Führer, who refused to watch the film for a full year. But when he finally saw the film in 1943, Hitler had a change of mind and authorized greatly increased funding for the development of ballistic missile capable of bombing London from the continent. The production of the Model A4, renamed the Vengeance Weapon II, abbreviated to the V2, appeared in service in September 1944. By then, D-Day was history. The Allies had recaptured Paris, and the first V2 launches were directed against both London and Paris rather than being concentrated on England. The V2 missile lacked an electronic guidance system and was woefully inaccurate, generally landing 10 or more kilometers from its target point. This meant that the V2 was ineffectual against military point targets, but it could be fired effectively against extended target areas, 20 or more kilometers in diameter. The only such targets available to the Nazis were urban areas. Thus, the V2 was incapable of servicing as a counterforce weapon, but it made a perfect terror weapon against civilian populations, and thus it's precisely how it was used. Fortunately, casualties from these attacks were light. The 4,300 V2 rockets fired against England caused only 2,500 deaths, almost all of them civilians. The large-scale military use of the V2s in the closing days of World War II demonstrated the reality of rocket propulsion. The dismantling of the German rocket program at the end of the war left the technical masterminds of the programs and most of the surviving missiles in American hands, although most of the factory personnel and equipment fell to Russians. Both sides assimilated what they could of the German rocket enterprise. but it was the Americans who got Werner von Braun. The rest of the design teams, the true brains of the operation. A number of captured and modified V-2s were launched at White Sands, New Mexico, and von Braun's team went to work in the United States Army Redstone Arsenal in Hudsonville, Alabama, designing short to medium range 10 to 500 mile tactical battlefield missiles. Opinion remained divided on the possible utility of intermediate and intercontinental range 1,500 and 5,000 mile weapons. As late as 1947, no less than an authority on the America's wartime technical genius, Vannevar Bush, the head of the U.S. Office of Scientific Research and Development, interpreted the performance of the V-2s over London as evidence that long-range missiles could not possibly hit point targets and hence were of no military significance. Other observers reached more practical conclusion that some means of controlling the flight of rockets were needed. They therefore advocated the development of electronic guidance systems for military missiles, beginning with a vacuum tube technology. Yet others of a more visionary turn foresaw the evolution of rockets into a device to deliver payloads into orbit around Earth, or to send them to the Moon and other planets. The German engineer Willy Ley wrote several books popularizing the idea of expeditions to the Moon and Mars, and he lit spark in the public imagination. In 1947, the Soviet Union initiated a program to design and build intercontinental range ballistic missiles. The post-war American ICBM program was cancelled by President Harry Truman at the urging of Werner Braun in the same year. For 6 fateful years, Stalin backed the Soviet ICBM program while the United States slept. Only the decision of the General Dynamics to continue ICBM development on a shoestring with its own funds prevented the Soviets from achieving an insurmountable lead. Finally, in 1953, American government funding for the ICBM development was restored by the Eisenhower administration. But by then, the Soviet program had a hefty lead that guaranteed them first entry into space, with the launching of Sputnik 1 in 1957. As the readers and writers of newspaper became aware of the rapid progress of rocket technology, editorial writers rather abruptly ceased writing, Pulitzer ridiculing space and its advocates, and commended writing glowing Sunday supplement articles lavishly illustrated, echoing the promise of space and the virtues of its practitioners. It also suddenly became possible to say kind words about space visionaries. For example, Arthur C. Clarke, a successful British engineer turned science fiction writer, had proposed in 1947 that satellites could be placed in orbit 40,000 kilometers above the equator, where their orbital periods of 24 hours would cause them to remain stationary in the skies as seen from the ground. These satellites, Clarke suggested, might be used for communication relays to bounce radio and television transmissions across the oceans and enable global telephone and telegraph services without reliance on transoceanic cables. With the launching of the first Earth satellites, Clarke underwent a near instantaneous transformation in the media from harmless crank to brilliant prophet. Another modest proposal of Clarke's, published in 1939 in the Journal of British Interplanetary Society, suggested that missions to Mars systems might be able to extract water and other volatile materials from the Martian moons Phobos and Deimos. These resources would then be processed to make air and water for the crew, and rocket propellants for use on landing Mars and taking off from Mars. Returning to Earth. The press generally ignored this suggestion. Perhaps it was simply too far out to be worthy of repetition. Other visionaries fared similar. The British physicist J.D. Bernal wrote in his famous essay The World, the Flesh, and the Devil in 1929 of the engineering of asteroids into vast hollow habits to hold immersed populations, carry them throughout the solar system, and eventually ferry them to other stars. He argued strongly that the cost of launching materials out of Earth's deep gravity well was prohibitive compared to using the resources already available in space. He was the first to propose that solar power could be collected in space and beamed down to Earth to power our industries. He envisioned vast hollow space habitats built of asteroidal material and powered by the sun, each engaged in the task of replicating itself and multiplying until the competition for sunlight became so severe they would embark on interstellar voyages to find new resources for growth. The extraordinary mind of the British science fiction writer Olaf Stapleton surpassed even this astonishing vision. In Last and First Men, 1930, he foresaw a vast panorama of future proliferation of mankind in space, giving rise by means of direct evolution to a new species, adapted to conditions on other planets. Space, Stapleton implied, was not just a list of dangers, it was a menu of opportunity. This reader may have noticed a peculiar coincidence. All three of these visionaries were British. It was in their brilliance and far-sightedness that stimulated the formulation of the Explorarian Biz. This society, though its meetings and publications has for over 60 years constantly advanced the cause of innovation and exploration in space, its membership, an eclectic mix of people with deep interest in space, spans the political and social spectrum and touches many nations. Yet strangely, the Biz has less influence on British space policy than its counterparts in the United States and Soviet Union. Perhaps the Biz members were so far-sighted that they lost touch with the mundane necessities of day-to-day political life. Certainly there has been little inspired and visionary support of space activities by the British government. Whatever the reason, it remains true that the greatest triumphs and aspirations of the spacefaring nations represent a remarkable degree their practical workout of the British dreams. One might suppose that the high water mark of space exploration to date, the Apollo program for exploration to the moon, was in part inspired and motivated by the idea of self-sufficiency in and profit to mankind from the energy and material resources of space. But this was not the case. The goal of the Apollo was not practical benefit, nor even scientific research, but political posturing. In the Apollo exploration of the moon, the concept of using lunar materials was intentionally avoided because of the engineering conservatism and managerial short-sightedness. The idea was to build a foundation for the future, but the idea was not to build a foundation for the future, but to get there quickly, boast about beating the Russians there, and then cancel the program to cut the losses. The capability to continue to explore space using the Apollo spacecraft and the Saturn boosters was swiftly destroyed once the political goal had been met. Preventing the space endeavor from evolving into some mere commercial, profitable, or curiosity-driven scientific venture that might take on a life of its own and escape government control. It is a measure of our time that the phrase commercial and curiosity-driven have again become projective, almost as damning as visionary. Apollo itself, widely touted by the press as visionary, was in essence a political act intended to make America look good compared to the Soviets, a particularly strong, focused reflection of the old Cold War. Our inheritance from Apollo was not the realization of a dream, but rather its end. But as long as human beings live, they will feel curiosity and engage in commerce. The only viable route to a future of growth is to allow these basic human activities to free rein. The only viable route to a future of growth is to allow these basic human activities free rein. What do we know then about the resources of space and how to use them? The scientific study of samples returned from the moon by the Apollo expeditions and the data sent back by a variety of American and Soviet unmanned missions have given us a vast library of information about the availability of resources on the moon. This will serve as an excellent place to start our survey on the resources of the solar system, the first halting step in a journey of exploration that will eventually take us very far indeed in both space and time.